Hi everyone and welcome. In today's video, I would like to motivate the need for the set of real numbers. And to do this, we will actually show that there is no rational number whose square is exactly 2. In other words, we will prove that the square root of 2 is an irrational number. And then we will discuss some of the consequences of this result and what impact it had on the ancient Greeks. But before we can prove this result, we will need to prove a basic lemma that we will use in this main proof. Let's prove the following statement. So let k be an integer. If k squared is even, then k must also be even. So this is a very basic result, and the way we are going to prove this is by using the contrapositive. So just to help you recall, if you have a mathematical statement p implies q, then the contrapositive would be not q implies not p. And if you remember, the contrapositive is logically equivalent to the original statement. So if we prove the contrapositive, then we end up proving the original statement. And so let's see what is the contrapositive of this statement. Well, it would be if k is not even, then k squared is not even. In other words, if k is odd, then k squared is odd. So this is what we are going to prove. And so what does it mean if k is odd? Well, if k is odd, then k can be written in the following form. It's 2 times some integer, let's call it m, plus 1. Right? So this is the definition of an odd number. It's just 1 more than an even number. Now let's consider k squared. So let's plug in 2m plus 1 for k and just square it. And then we can FOIL out and we get 4m squared plus 4m plus 1. And remember, our goal is to show that k squared is odd. And so what I want to do is actually write it in this form. I want to write it as 2 times some integer plus 1. And it's actually pretty easy to do here. We just need to factor a 2 from the first two terms. So if I do that, you see I get 2 times some integer plus 1, right? And the inside is an integer because m is an integer. So if I square it and multiply it by 2 or do 2 times m and add that to the result, this is all integers. And so yeah, we have 2 times some integer plus 1, and that shows that k squared is odd. And so that also proves the original statement. And so now I would like you to keep this in mind as we go along with the rest of the video. Okay, so now let's prove the main result, that there is no rational number whose square is 2. And to do this, we will argue via contradiction. So let's suppose for contradiction that there is some rational number, let's call it r, that does satisfy r squared is equal to 2. Well then, what does it mean for r to be a rational number? Well, it means that r is just the ratio of two integers, right? That means r can be written as p divided by q for some integers p and q, and of course q is non-zero. And any rational number can be written as a fraction in many different ways, but what I want you to do is actually make sure this is in lowest terms. So if this was not in lowest terms, then we can just cancel common factors so that it is in lowest terms. And so we will also insist that p and q have no common factors. And so just to reiterate this point, because this will be important, is that any rational number can be written in lowest terms, and that can be done uniquely. It's going to have a unique representation, right? So if this wasn't in lowest terms, well, we can just cancel common factors, and we will get an equivalent representation for the same number, just that it's in lowest terms now. Okay, great. So now moving along, let's plug in this representation p over q into this equation, r squared is equal to 2. So when I plug that in and I simplify, I can just distribute the square on both the numerator and denominator, and then I can also bring the q squared to the other side. I get this equation, p squared is equal to 2q squared. And now check this out. What we have on the right hand side is 2 times some integer, right? Q is an integer. If I square it, that's also an integer. But what I have is 2 times some integer, and 2 times some integer implies that the left hand side must be even, right? If the right hand side is even, then that implies that the left hand side should also be even. So in other words, p squared must be even. But now remember the result that we just proved. If p squared is even, then it must be the case that p is even, right? So it follows that p is even. So then we can actually let p equal 2 times some integer m. Okay, so now let's go back to this equation. And actually, let's work with this one here. P squared is equal to 2q squared. And let's plug in this representation that we have for p. So instead of p, I'm going to put 2m here, and I'm going to simplify. So p squared is just equal to 2m squared, which is equal to 4m squared. And all of this is equal to the right hand side, which is 2q squared. And so now notice over here I can divide both sides by 2 and I'll get 2m squared is equal to q squared. And now notice again, on the left hand side I have an even number, right? 2 times some integer, that's an even number. So that implies that the right hand side must also be even. That is, q squared must be even. And now we again apply the result that we proved at the beginning of the video to say that q must also be even. But now we have a small issue. We have that both p and q are even. So that means that they're both at least divisible by 2. And so they have a common factor. Whereas we stated that p and q should have no common factors, and if they did, we first canceled them out and made the fraction in lowest terms. But we end up finding that in fact, even after doing that, they still have common factors, right? So that's a contradiction. And so what that means is that the original equation that we were trying to solve, which is this p over q all squared equaling 2, well, this cannot hold for any integers p and q. And so that proves the result that there is no rational number whose square is 2. Next, I would like to give you a bit of historical context and the significance of this result. So this result had a huge impact on the ancient Greeks, who believed that the rational numbers were a perfect number system. Well, back then they didn't have this concept of the rational number system, but they believed that all quantities could be expressed as just ratios of whole numbers. And what they also believed was that there was a perfect correspondence between geometric lengths they could draw and arithmetic number. That is, no matter what length they drew, they could always assign it a number, and every number corresponded to a constructible length. But now I would like you to consider the unit square, which is basically a square with all side lengths equal to 1, and consider the length of the diagonal. This is a length that the ancient Greeks could draw or construct, but they weren't able to assign it a number. This quantity right here could not be expressed as a ratio of 2 integers. In other words, this length had no associated number. And so this is why the discovery of the square root of 2 not being a rational number shook the foundations of mathematics for the ancient Greeks. And they weren't able to come up with a satisfying solution to this problem. And so as a result, ancient Greeks had to accept numbers as a weaker notion than geometric length. And so the Greeks shifted mathematics to focus more on geometry, and geometry became this primary framework to avoid dealing with irrational quantities directly. And this theme can actually be seen in many influential works at the time. A great example would be Euclid's Elements, which is a very important book, and it's a cornerstone of even mathematics today. And this is a book on geometry that focuses on explicit constructions using compasses and straight edges. And it wasn't until much later that mathematicians were able to properly address and overcome the limitations of numbers by expanding to a new larger number system. And so now let's take a quick step back and look at the bigger picture. Let's see how extending to a larger number system actually solves our problem. So let's start with the set of natural numbers, which are basically the positive integers. So the set of natural numbers is denoted with this special n, and these numbers, we can use them to count and add. But what if we also want to subtract numbers? And so what we do is we naturally extend the set of natural numbers to the set of all integers, in which we add in 0 and we add in all the negative integers. And so now this set of numbers allows us to also subtract quantities. But now let's say you wanted to maybe divide and take ratios of quantities. And so we're limited in this number system. And so what we need to do is further extend to the rational numbers. The set of rational numbers is denoted by this q, and it's the set of all numbers of the form a over b, where a and b are integers, and of course b is non-zero. And so these set of numbers we can use to of course add and subtract, but now we can also multiply and divide. And now discovering that the square root of 2 is not a rational number, we see an issue with this set of numbers, which is that it has holes or gaps. So I want you to consider the number line, in which we have 0, we have all our positive integers, our negative integers, and we have all our rational numbers like 1/2 and 1/100th and 1.5 over here. But this number line is actually incomplete. It's going to have small holes and gaps. So for example, around 1.4, there's actually a hole or a gap. And so this is an issue, because if I was to draw a length of this size, then I would not be able to associate it with a number. And so what I want to do is actually fill in these holes and gaps. And so the natural thing to do would be to actually further extend our number system, right? So we started with the set of natural numbers, we extended to the set of integers, then we extended to the set of rational numbers, and now let's extend one more time to the set of real numbers. And the way we denote it is by this special looking R. So right now, the way I want you to think about the set of real numbers is actually a natural extension of the set of rational numbers. So it's going to include all the rational numbers along with the integers and the natural numbers, and it's also going to preserve all the nice algebraic and order properties that you're familiar with, but it's going to have some new numbers, namely the irrational numbers, that are meant to fill in the holes or gaps that the set of rational numbers have. And we would like to mathematically capture what we mean by filling in these holes and filling in these gaps. And to do this, we will have to introduce a new assumption or a new property of the set of real numbers that the set of rational numbers does not have. Otherwise, there would be no difference between these two sets. So this set, the set of real numbers, they need to be fundamentally different. They need to have some new properties or some new assumption that's able to capture this filling in the holes and filling in the gaps so that it does form a complete number line. And so this is what we will be working towards in the next few videos. In the next video, we will take a closer look at the set of rational numbers and the set of real numbers. Specifically, we will look at some of the properties they share and why they share those properties. And we will see that they both share these familiar properties because they happen to be something called ordered fields. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.